In this video, we are going to now discuss the mean value theorem in higher dimensions. As we have seen earlier, the straightforward generalization of the mean value theorem is no longer true for vector valued functions of a scalar variable. The version I am going to present is actually an inequality, and it works for differentiable mappings from any open set in Rn to Rm, so between arbitrary Euclidean spaces. So the theorem is as follows. Theorem: let f from U to F be differentiable. And let a comma b be points of U. Define the function L of t to be nothing but ta plus 1 minus tb. This is nothing but the line segment joining A and B. Suppose this entire line segment L of 0, 1 is fully contained in U. Okay, and furthermore assume that the operator norm of the derivative is less than or equal to some constant k, for all x on L of 0, 1. Okay, on this line segment, suppose the operator norm, there is a uniform bound capital K. Then norm f of b minus f of a is less than or equal to k times norm b minus a. So there is now an inequality. The usual mean value theorem said that there will be a point such that f of b minus f of a is equal to df of x times b minus a. That is no longer true in general. We have already seen a counter example, but this inequality will be more than sufficient in most applications. Let's see a proof. So by openness of U, we can actually find a small epsilon greater than 0 such that this entire set 1 minus ta plus tb such that t comes from closed minus epsilon to 1 plus epsilon. This whole thing is a subset of U. That is, we have assumed that the line segment, so if this is U and this is A and this is B, so this is A and this is B, we have assumed that the line segment joining A and B is contained fully in U. What I am saying is you can extend this line segment a bit further on both sides. That's essentially what I am asserting, and this will follow from the openness of U in a straightforward way. So we can view this function L from minus epsilon 1 plus epsilon to U. There is still no issue. It will still map into U. It will not take it outside U. Okay. So if f of b equal to f of a, we are done. Nothing to prove. So that takes care of the trivial case. Okay. So assume f of b is not equal to f of a, and set the vector u to be f of b minus f of a by norm f of b minus f of a. That is the unit vector in the direction f of b minus f of a. Okay. Now we are going to define a new function g. From minus epsilon 1 plus epsilon to this is just going to map to the real numbers. This is as follows. G of t is just this vector u dot product, the standard dot product, f of L of t minus f of a. Okay. So here of course dot is the standard inner product. The standard inner product. So we have manufactured a function that maps this interval minus epsilon 1 plus epsilon to the real numbers. Okay. Now it is elementary that the function g is differentiable. It's differentiable. This follows from the various properties of the derivative map that we have already established. This proves that from those properties you can conclude that g is differentiable on minus epsilon 1 plus epsilon. This is differentiable as a usual classical one variable function, and is also continuous. Because it's differentiable, is also continuous on close 0 1. Okay, excellent. And from the properties that we have seen, it's easy to see that the derivative g prime of t is going to be u dot product df taken at the point L of t, and this df taken at the point L of t acts on the vector L prime of t. Okay, this is going to be the derivative. This is just an application of that product rule that we have seen, and noting that u is just a constant, it's just a constant vector. Okay, so this is just equal to u of u dot product df L of t, and remember L of t was 1 minus ta plus tb, and the derivative of that is as a vector function is nothing but b minus a. It's nothing but the constant vector b minus a. That's to be expected because L of t is actually just a line segment. It parameterizes a line segment. The derivative is b minus a. Okay. So what have we got from all of this? Well, we have got, by taking modulus on both sides or the absolute value, we have got mod g prime of t is equal to the absolute value of u dot df at L of t acting on b minus a modulus. Okay. Now this by Cauchy-Schwarz inequality is just less than or equal to norm u times, here this dot is just times, okay, it has nothing to do with the dot product, df L of t acting on b minus a. Okay. And now by using the basic properties of the operator norm, this is less than or equal to norm u, which I can get rid of because norm u is a unit vector, remember that. So this is less than or equal to df L of t operator norm times norm b minus a. Okay, so this is one of the properties of the we have used the properties of the operator norm. Okay, so we get that mod g prime of t is less than or equal to the operator norm of df at L of t times norm b minus a, and now we can use this fact that the operator norm on L of t is bounded by this constant k to write it as k times norm b minus a. So apply the classical mean value theorem, to G, which we can because G certainly satisfies all the hypotheses. The endpoints we are choosing are 1 and 0. So mod G of 1 minus G of 0. Recall that G was defined by this expression u dot f of L of t minus f of a, and u was f of b minus f of a by norm f of b minus f of a. So what happens is when you plug in t equal to 0 in this definition, you get f of a minus f of a, simply because L is supposed to be the line segment that joins a and b. So you get a grand 0, and f of 1 is supposed to be f of L of 1 minus f of a, which is just f of b minus f of a. So you have got u dot f of b minus f of a, and u was just f of b minus f of a by norm f of b minus f of a. So the net upshot is g of t minus g of 0 will be nothing but norm f of b minus f of a. Okay. So what does the mean value theorem say? Well, this is going to be modulus of g prime of t naught times 1 minus 0, which is just 1, where t naught lies somewhere in between 0 and 1. So there is some point in the open interval 0, 1 such that this happens. So the net upshot of all this is the fact that combining these two, we get more norm of f of b minus f of a is less than or equal to k times norm b minus a as asserted. Okay, so this concludes the proof of the mean value theorem. So in the exercises, you will formulate a version of the mean value theorem that does not involve an inequality, at least for real valued functions. It's not that hard. You just look through the idea here. You can also formulate a general version of the mean value theorem that does not involve an inequality by observing what we have done here. But that is not very useful. This inequality, final inequality that we get, is more than sufficient for applications. This is a course on real analysis, and you have just watched the video on the mean value theorem.